Hi everyone! In today's lecture we're going to cover two more reactions. The first one is nucleophilic aromatic substitution. So far we've been discussing electrophilic aromatic substitution where the benzene ring acts as a nucleophile and then it attacks an electrophile. But here we're going to reverse that. The benzene ring will act as an electrophile, and it will be attacked by a nucleophile. All right, so let's look at an example of nucleophilic aromatic substitution. So here we have our starting material, and we're going to react this with a nucleophile. In this case, the hydroxide ion, and we'll follow that up with some dilute acid. And then what ends up happening is the leaving group bromine is replaced with that hydroxide ion. All right, so there's a few things that must be true in order for a nucleophilic aromatic substitution reaction to occur. First, you need a good leaving group. So in this example, the leaving group is bromine. Next, you need to have a strong deactivator or electron withdrawing group. And we'll see why we need that strong electron withdrawing group on the next slide. Finally, the leaving group should be ortho or para to the electron withdrawing group. So we'll also talk about that on the next slide. Okay, so let's go over the mechanism for this reaction. So let's start with that same starting material that we saw on the last slide. And I'm going to draw NO2 out just so we can see where electrons are moving. All right, so again, in the first step, that nucleophile is going to attack the benzene ring. So it's specifically going to attack the carbon next to the leaving group. That will be partially positively charged. Now, the leaving group doesn't leave right away like we would normally expect, right? This is actually going to cause the pi electrons next door to move over to a neighboring carbon. And this is going to create an intermediate where we have a negative charge on one of the benzene ring carbons. Of course, it's not really a benzene ring anymore, but you get the idea. Okay, so this intermediate is called a Meisenheimer complex. And notice that this is different from our sigma complex, or also known as an rhenium ion. So remember, in a sigma complex, we have a positive charge on the ring. In this case, we have a negative charge, so this is different. Now, what's great though here is that negative charge can move down the ring all the way to oxygen. So now we have two negatively charged oxygens. And that nitro group is really acting as a place where electrons can sit and hang out, which is going to stabilize this intermediate. So this resonance structure is allowing the added electrons from the nucleophile to kind of go down and hang out with our electron withdrawing group. So if that nitro group was in the meta position, for example, this wouldn't work. We would have a very unstable intermediate. So that's why the nitro group and the leaving group have to be either opposite each other or right next to each other. So if we go back, remember the leaving group must be orthopara to the electron withdrawing group. And that's due to the intermediate. So that positioning stabilizes the intermediate. So again, if that nitro group was in the meta position, we wouldn't see a reaction because the intermediate wouldn't be stable. Okay, so now in the next step, and I'll draw the arrows in blue for this next step, our electrons are going to move back up, but they're going to go to the opposite side here, and there's going to be kind of a cascade of movement with these electrons. And that's going to kick out this leaving group. So now we're just left with the alcohol group. Oops, and actually let me draw these electrons in the appropriate place. They're delocalized, but we should try to be consistent. My pen's freaking out. Okay, there we go. All right, so unfortunately in this reaction we have excess nucleophile which could act as a base. So that excess nucleophile can take that proton on our alcohol group. So that means we end up with a negatively charged oxygen. So to reprotonate that oxygen, we're going to add some acid. And that's just going to add a proton back onto our oxygen, and now we have our final product. Okay. Now, the other reaction we're covering today is called elimination addition. So if we, for instance, don't have a strong electron withdrawing group on our benzene ring, but we still want to, let's say, replace a leaving group with a nucleophile, unfortunately, this reaction just doesn't work. So that's just due to the fact that there is no electron withdrawing group on the ring. However, we can achieve this reaction if we increase the temperature. So if, for instance, we add heat, and we'll just draw a little delta symbol there for heat. Now suddenly this reaction works. and we can replace that leaving group with a nucleophile. However, this reaction is very different from our nucleophilic aromatic substitution reaction that we just saw. It goes through a completely different mechanism, so that's why this is referred to as elimination addition. If you use a stronger nucleophile, you don't need these high temperatures. So for instance, let's say instead of the hydroxide ion, we use sodium amide. So the amide part, NH2 minus, that would be our nucleophile. And that would be mixed with ammonia there. And the amide group, NH2, would replace that bromide. And you only need moderate temperatures for this reaction because of the strong nature of that nucleophile. So again, if you don't have a strong electron withdrawing group on the ring, but you're still attacking that benzene ring with a nucleophile, we call that elimination addition. All right, so let's look at the mechanism for this reaction because again, it's very different. So in this reaction, and let's use the example where we try to replace this bromine with NH2. So the NH2 is going to actually grab onto a proton. And it's going to grab onto a proton next to or on a neighboring carbon. And then the shared electrons between hydrogen and the carbon will be left behind, and then the leaving group will leave. So notice we end up with a triple bond, and this is called benzyne. Now, this triple bond does not last very long. It is not very stable. So in the past, we've said you can't have a triple bond in a ring this small. It just doesn't work. However, it can exist for a very brief amount of time, but it's so unstable that it will react pretty much right away. Now, there are two sides to that triple bond, and we can add our nucleophile to either side. So to show the two sides, I'm going to add a methyl group at the bottom here, just so we can kind of see the two different outcomes better. All right, so in our first possible product or possible reaction, NH2 could attack at the position to the right, and that's going to move pi electrons over to the carbon on the left of the triple bond. All right, so then we end up with NH2 at the top and a negative charge on the neighboring carbon. So NH2 added para to the methyl group. And then in the last step, we're just going to add some dilute acid, so H3O+, And that negative carbon is going to grab onto a proton, and we get our final product. Okay, the other option is NH2 could attack the carbon on the left of the triple bond, and then that would leave electrons on the carbon on the right. So now NH2 has added to the meta position instead of the para position. And again, we would add acid just to reprotonate that carbon. And we get our second product. Oh, let me fix my H there. It's a little messy. Okay, so we have two different products here. So again, we have a very different mechanism for elimination addition reactions. And we have very different intermediates as well. So in our nucleophilic aromatic substitution reaction, our intermediate was the Meisenheimer complex. And in our elimination addition mechanism, our intermediate was benzene, where we had a triple bond in our benzene ring. So again, for nucleophilic aromatic substitution reactions, you need a good leaving group and a strong electron withdrawing group. If you don't have that strong electron withdrawing group, then you're going to have to either increase the temperature of your reaction or use a stronger nucleophile, and this will go through an entirely different reaction called elimination addition. All right, so that's it for this chapter. If you do have any questions, please feel free to set up an office hour with me using the Calendly link on the main page of Canvas, or you can always come to my regularly scheduled office hours or message me on Canvas or by emailing me